Hi everyone. In this recording, we're going to look at limits at infinity. This is going to be the first of at least one recording on this topic. So this is looking at the definition from the OpenStax book. All right, we're talking about the limit of a function if it gets arbitrarily close to a fixed value. All right, we're going to write the limit as x approaches infinity or x approaches the negative infinity of your function is going to equal that fixed value. Graphically speaking, we know that this is just saying the graph has a horizontal asymptote as x approaches positive infinity or as x approaches negative infinity. Right, so again, positive infinity going to the right, negative infinity you're going to the left. All right, and we're leveling out, the graph is leveling out at whatever those values are. We're going to look at a couple basic facts, all right, to start us off. All right, one, the limit as you go to positive or negative infinity of 1 over x is 0. Similar for any positive power, 1 over that power will go to 0. Let's quick look at that graphically. Okay, so I'm going to go over to Desmos, and I've got 1 over x plotted here. All right, and we know if we keep going to the right, 1 over a larger and larger number is going to be very small. 1 over a large but negative number is going to be negative, but closer and closer to 0. All right, if we look at 1 over x squared, very similar looking graph going left to right, it levels out at 0, gets closer and closer to y equals 0. This time the graph, though, is all above the x-axis because when we square any negative number, this becomes positive. And similar for any other 1 over x to a positive power. Some other basic facts for polynomials. All right, if we have an even power, then you're going to go to infinity going both left and right. All right, and we know that from our graph of x squared, x to the fourth, as pictured on the screen here. All right. Let's try to scroll down just to here like that. Okay, they're all sort of U-shaped. As the power gets bigger and bigger, it's going to flatten out a little bit near 0, but we're going up to the left and up to the right. So we're just going to write that the limit as we're approaching infinity or negative infinity of these functions is positive infinity. Similar but slightly different for odd powers. My spacing got a little bit messed up here, so I'm just going to fix that. All right, we know what the graph of an odd power function looks like. All right. Thinking about x to the third or x to the fifth, x to the seventh, and so on. They go down to the left, up to the right. So this is a little bit different in that you're going to be approaching a positive infinity as we're going to the right, towards positive infinity, and the limit will be negative infinity, all right, as we approach negative infinity as we're going to the left. Okay, these are some basic facts that we know. All right, now let's think about the end behavior for polynomials. It turns out that the end behavior of a polynomial matches the end behavior of its leading term. So I'm going to do a little bit of work to show this, and then we will look at this graphically. So what's our leading term? Our highest power of x term is negative 4x to the third power. So I'm saying, okay, that matches what the end behavior of just that function is. All right, and we should know that, just roughly speaking, on a large scale, this is going to be an upside down cubic. All right. And so our end behavior should be looking like that. All right, so we should definitely be seeing that we're approaching negative infinity as we go towards negative infinity, as we go towards positive infinity, and positive infinity as x goes to the left towards negative infinity. I want to do a little bit of work to show this algebraically, and this is going to translate over to what we're doing with rational functions right after this, and it's by factoring out the negative 4x to the third power. So I'm just going to rewrite this a little bit. So we have the limit as x approaches positive infinity. Now, if we take out the leading term, which is negative 4x cubed, we're left with 1. All right, just 1, and then this will be minus 2x squared over 4x cubed. The signs are going to change there. Minus 1000x over 4x to the third power, and then minus 1 over 4x to the third power again. All right, now, after we simplify these expressions briefly, what's that going to look like? Well, we can divide out the 2's, we can divide out the 4's, and divide out the x's. So just rewriting this one more time, we're going to have the limit as x goes to infinity, keeping the negative 4x to the third there. We're going to have 1. This would be minus x squared. Well, 2 of those factors are going to cancel. We'll have 1 over 2. 2x's on top, cancel a 2 on the bottom, so it's 1 over x. 4 goes into 1,000, 250 times. Again, we're canceling out 1 of the x's with 1 of the x's in the bottom. In this case, it's going to leave us with x squared in the denominator, and then the last term is just the same. All right, now why is that showing us that the end behavior is the same as the leading coefficient? Well, because all of these individual terms here that we're underlining, they're all going to approach 0 as x approaches positive infinity. Right, so we're really getting just the action of the negative 4x to the third power on a large scale. Very similar to what we would see as we're going towards negative infinity. All right, so it's going to match that. So what we would write here is that this limit, as we saw graphically, this limit will come out to be, in this case, going to the left, it will be positive infinity. All right, the limit as we're going to the right will be negative infinity. And I want to just look at the graph real quick for this one. Okay, I'm going to go over to Desmos to do that. All right. Okay, and I've got the original function here graphed in kind of just the normal viewing window, negative 10 to 10. And in my next tab over, I have it graphed by changing that window quite a bit. So it's the same function you can see plotted. The reason it looked kind of weird in the normal viewing window is because that 1000x is kind of dominating the action when we're talking about small x values. If we zoom way out and notice my scale on my x-axis does not match even close to my y-axis scale, but this goes along with the idea that the leading or the end behavior will be dictated by the leading term. So if we zoom out far enough, it's going to look like negative 4x to the third power, and we can keep zooming out here, and it will look more and more like negative 4x to the third. Okay. All right. Now let's talk about the end behavior for rational functions. Okay, and we're going to do some of this graphically. We're going to do some of this analytically. All right, or algebraically. Now, the way we're going to be doing it algebraic, let's do that first, and we'll do that with these first couple examples, is we want to divide the top and bottom, and each term in the top and bottom, by the highest power of x in the denominator. So in this case, we're going to divide the top and bottom by x everywhere, each term by x. All right, simplifying that just briefly here, while 1 over x we can't do much with, there's not much we can do here, except the x's will cancel in the first term in the denominator just to give us 5 plus 6 over x. And then we're going to use our properties of limits. We know 1 over x is going to approach 0, and 6 over x are going to approach 0 as x approaches infinity, and therefore this overall limit will equal 0 over 5, which is 0. Okay, so in this case, the limit is 0. Probably not too surprising here. For this next one, I'm just going to write the result that we get by dividing everything by x squared. All right, similar result would be if we're going towards negative infinity, we have to be, for these two examples here. So we divide everything by x squared. What are we going to get? We're going to get 1 over x minus 1 or 8 over x squared in the top. In the bottom, the x squareds are going to cancel in the first term. One of the x's will cancel one of the x's in the second term, and then we'd have 7 over x squared. And again, what we're seeing is all of the terms except the 3 are going to approach 0, and therefore this overall limit is going to be 0 over 3, which is just 0. Okay, well, why this is happening, the degree on top is less than the degree of the polynomial on the bottom. The reverse will happen in my third example here. All right, and I mentioned we could do this by using polynomial long division, or we could divide the highest power of x in the numerator, divide both, top and bottom by the highest power of x in the denominator. So let's do that part first, and then we'll look at the long division after that. All right, I just paused the recording to write out that division. So if we divide the top and bottom, and each term in the top and bottom by x, we're left with 3x plus, should have been just 2 here, not 2x, and then plus 7 over x over 1 minus 8 over x. And all the terms that have x's in the denominator are going to approach 0, so we're essentially saying that this limit's the same as the limit of 3x plus 2 as x approaches infinity, which will be positive infinity. If we were going towards negative infinity, we should note that limit would be negative infinity. All right, let's look at thinking about doing this with polynomial long division quick, just as a reminder of that process. So we'd have 8 minus x, and we're going to divide that into 3x squared plus 2x plus 7 All right, so we're going to ask ourselves what times x would be 3x squared, and the answer to that would be 3x. So we'd multiply the polynomial 8 minus x by 3x, and we'd get 3x squared minus 24 x, and then we'd subtract. That would give us 26x plus 7. And then continuing, we'd have to ask ourselves, okay, what will we multiply x by to get 26x? All right, so then that's going to be 26. All right, and multiplying that polynomial by 26, we're going to get 26x minus 8 times 26. And 8 times 26 is 208. That's giving us a remainder. Once we do the subtraction, we're going to have 7 minus negative 208, which is coming up to 215. All right, now what is that telling us here? This is telling us that this ratio, 3x squared plus 2x plus 7, when we divide that by the polynomial x minus 8, it can be written as the whole expression, or the whole polynomial 3x plus 26, and then plus the remainder, which is 215, divided by the divisor, which is x minus 8. All right, and that just goes to show that the slant asymptote, or the oblique asymptote in this case, would be 3x plus 26. If the degree on top is 1 more than the degree in the denominator, then we end up having a horizontal, or not horizontal, but a slant asymptote. So as x gets bigger and bigger, we're going to get closer and closer to this line, 3x plus 26. Doesn't change the fact that the overall expression is going to be approaching infinity as x is approaching infinity. This is going to approach infinity. This is going to approach 0 as x approaches positive infinity. All right, let's just look at that one graphically. Okay, so I have the function graphed here. And notice if I go just to the standard viewing window, not a lot of it shows up initially in your negative 10 by 10 kind of starting point window. But if you zoom out enough, you'll start to see what that graph looks like. And if I put on the line y equals 26x, 3x plus 26, excuse me, then we can see that as x gets bigger and bigger, going towards the right, we get closer and closer to that graph. All right, going towards the left, it'll get closer and closer to that same line. Again, it becomes asymptotic to that line. Before we move on, I had the other ones graphed here as well. All right, so this one was the second example. This gets closer and closer to 0. This one was the first example. As we go to the right or to the left, we get closer and closer to 0. The next example we're going to look at is this one. So let's look at it graphically first. Then we'll go back and analyze it algebraically. We can see this one, if we go out far enough, it levels out at a fixed value. So we're going to look at that right now algebraically. Again, we're going to take the same technique that we've been using by dividing the top and the bottom by the highest power of x in the denominator, which is x squared. I'm going to pause and do that division. All right, so dividing the top and bottom by x squared, we'll get a simplification. All right, remember, you got to distribute the division to each term of 5 plus 7 over x squared, and then 3 minus 1 over x. Now, clearly, these couple of terms, oops, scroll back down here. Clearly, these two terms where we have the x's in the denominator, both of those are going to approach 0 as x is approaching infinity, and therefore, we're just left with 5 on top and 3 on the bottom. And if we go back and graph that, that is going to be the horizontal asymptote. So it depends, right? And the fact is, if we're looking at rational functions, the end behavior is the same as the ratio of the leading terms. So you take the leading terms and ratio them out, and that will determine your end behavior. And that's going to depend on whether the degree on top is bigger than the degree on the bottom. If the degrees match, you're going to have a horizontal asymptote like in the last example. If the degree on top is smaller, it's going to be y equals 0, or the x-axis. If the degree on the top is larger, then that depends on the signs of the leading terms, and it's either going to go to positive or negative infinity. So again, it depends on how this expression highlighted simplifies, what the signs of these numbers are if your degree on top is bigger than your degree on the bottom. If they're equal, it'll be the ratio of the coefficients because the x's will completely cancel out.